Hello everyone, welcome back to the CAE-SHOP channel. Today, I will introduce a simple sloshing problem done by two methods using Lagrangian and arbitrary Lagrangian Alesian method. Of course, to decrease the flute, arbitrary Lagrangian Alesian method will be better. But in this video, I still want to keep two methods to see and compare the result. The model will like it. The free surface or the top face here is not in a stable position. The left side is higher than right side. It vibrates freely, so it is only affected by gravitational acceleration. Okay, let's do it. I will use a speculum to draw the sandwich. I will draw the sandwich in the xy plane, so I will need to change the base plane to the xy. Normal view in the z direction and draw a rectangular shape like this. And use the dimension to determine the length of each side. The width equals 100 mm. The left side is 110. And the right side is 90. And sketch editing. And extrude the model in the z direction 10 mm. Okay. Close the sandwich. We need to define a new material. Double-click on engineering data. Click here to add a new material. I will use the default name is matte null and use the model matte null here. Density equal 1000 kg per meter cubic. Pressure cutoff is -1 even. And define an addition equation state. Model here is a correlation. Value for C coefficient is 100 meter per second. Close the material. Double-click on model cell to open mechanical window. First, we need to change material for the body. Default material is a structure steel. We need change to matte null defined. In the matte plane, I will define 10 elements on X-axis. Here, I will have 4 axes. In the matte plane, insert a sizing. Change type from element size to number of division. Enter 10. Capture curvature no, and behavior is hard. I will insert more a face matching for front face for the better match, and use a sweep method for body method sweep. So anti-this direction is the automatic thing. If we create only one element in the technique direction, right-click and select Generate Map. Okay. We define boundary condition. The wall around the water is not defined, so we need to constrain some degree of freedom around the body. First is the two-phase in the z direction. Two-phase. Insert development and define the z component equals 0. Next is the two-phase in the x direction. Development x component 0. And the bottom phase is 0 in the both three directions. Therefore, the section control for solid element is a constant solid, so we can define or not a section control. So here I will define a section control. Apply for this body. Then in the next analysis, we can use this section control to enchant the method to another method. Here the method is defined with a finite element. Formulation is a constant just solid element. And in analysis setting, I will consider the problem in 2 seconds. For this time, I will reduce the safety factor to 0.7. Use 4 CPUs, depend on the hardware. In this problem, you can see the math is very cold. It will cause the hourglass mode. So to reduce it, we need to use a hourglass control. In analysis setting, we have hourglass control. Default type is a program control. I will use a standard LS-DYNA. You can use a hourglass control. We will generate an artificial energy. It's not a good energy, so we need to control coefficient here, so that the artificial energy is more enough. First, I will try with a more coefficient. Is 1 e minus 6. Then we need to define another control energy. Select LS-DYNA brand on the menu. Click on Add-on Start. Active keyword manager. Click on Time. Back to the environment. You will have keyword manager. Find the keyword control energy and click on Add button. Here, hourglass energy default is not compute. I will change to compute it and include in the energy balance. The body is vibrate freely, so we only need to define a load. Here is the standard Earth gravity. The direction is the minus y. Direction minus y. Okay, that is enough. We can solve the problem. You can see the time step is reduced degree too small. So you can check update a result. We know the solution information you can have total information here. You can right click and select update result. Or you can see the maximum deformation exit time is about 1 meter. It's not good, so I will stop the problem. Right click on solution to insert a total deformation. Right click again and retrieve the result. You can see the deformation is increased too much. At the current time is about 2 meter. Back to the analysis setting. Here I will increase the Howard coefficient to 0.01 and increase the result point in the output control. We have calculated result. Default is a program control. Switch to equally spaced point, and if phi is a 100 result point. Let's solve the problem again. And see the result. Total deformation. You can see here we have some oscillation. The magnitude after X oscillation is reduced. Let's check the energy. You can select the solution information in the solution output here. Default is the solver output. You can change it to energy summary. You can see here is the kinetic energy. It is reduced after X oscillation. Okay, it looks good. But you can see here another is a red line here. Is a Howard energy. It's increased too much after X oscillation. It's very low after 1, 2, 3, 4, after 4 oscillation. At 5 oscillation, at 5th oscillation, you can see the Howard energy is larger than. It is not good. It recommends that Howard energy is more relative to the peak internal energy below 10%. So here, internal energy is a purple line here. It's Howard energy is too large. So the result is not good. The next, we will consider the problem when use the arbitrary Lagrangian method. The problem on setting for the problem is the same. So on this window, you can right click on LS-DYNA and select the right click and select the duplicate. It will keep all settings as the same with the previous analysis. Now we only need to change the section control from finite element method to arbitrary Lagrangian ALE. Formulation default is the ID file. Now we have some other control in analysis setting. ALE control continuous treatment. I will change to the default advanced logic. Use the first order accurate. For simple average weighting factor, -1 will ignore this option, this feature. I will change it to 1. Use a small overlap coefficient. 1 is -6. And we'll consider the problem in 5 seconds. Okay, let's solve the problem again. Here you can see the kinetic energy is reduced after each oscillation, and Haugeland energy is very small. On this graph, I can see the red line. Check the total deformation. It will have some oscillation, and the magnitude is reduced after each oscillation. You can right-click on the solution information branch to insert a kinetic energy, apply for this body, and another internal energy. And the last is the Haugeland energy. Right-click and evaluate all these now. Here is the Haugeland energy. Its increase follows the time, but the value is very small. You can compare Haugeland energy with internal energy by control and select to energy. You can see here. The bottom line is the Haugeland energy. It is very small to compare with internal energy. It is acceptable. In the case of using AL in arbitrary Lagrangian ALE, you can see that is a marked improvement. Of course, to get accurate result, many other factors will need to be considered. Hope you will find it will have useful information after watching the video.